and the topic of potential functions and conservative vector fields. Here you have visualizations of vector fields in 2D or 2-dimension. As you can see, these vector fields in 2-dimension are represented by these small arrows. We want to connect a scalar function, potential function, with a field or a vector field. In connecting them together, we have some basic definitions and criteria. A vector field like F is called a conservative vector field if it is the gradient of some scalar function. It means that if there exists a function, scalar function like F, such that your vector field or vector function is equal to the gradient of the scalar function. In this case, F or the scalar function is called a potential function for vector field or vector function F. Please note that not all vector fields are conservative, and you're going to see such fields in physics and engineering. Also remember that now that we talked about nabla F or gradient of F, the gradient in 2-dimension is defined as follows. Suppose F is a differentiable function at point x and y, then the gradient of F at point x and y is a vector values function. So please pay attention. We started from a scalar function and we can define a vector function out of it by defining the gradient of F or nabla F, which is equal to, since we have a vector field, vector function, we need to use vector notation. The very first component of this vector is partial derivative of F with respect to x, and the second component of this vector function is the partial derivative of F with respect to y. You can rewrite this as well. It is equal to the first component of the vector times I in the direction of x-axis plus the partial derivative of F with respect to y in the direction of y-axis. And please note that this is just 2-dimensional gradient. In 3-dimension, you have f of x, y, and z, and you need to add the third component, partial derivative of f with respect to z. And on the last part, you're going to write plus partial derivative of f with respect to z times k, or in the direction of z-axis. Is there a shortcut here? That depends on the region. Suppose f is equal to pi plus qj, and it's a vector field on an open, simply connected region D. A simply connected region can be visualized this way. And also please note that when we are talking about a simple curve, it's a curve that doesn't intersect itself. Also suppose that these two scalar functions, p and q, have continuous first-order partial derivatives, and throughout the region D, the partial derivative of p with respect to y is equal to partial derivative of q with respect to x. This is the part that students usually make a little bit of challenging mistakes. You take the partial derivative of p with respect to y, you take the partial derivative of q with respect to x. If this equality holds, then you say that, hey, you have a conservative vector field. For example, check to see if the following vector field, which is defined as, please pay attention, for vector field, we use capital letter F or bolded letter, or we use an arrow on top of it, which is defined as x minus y in the direction of x-axis plus x minus 2 in the direction of y-axis. So basically you have your P and you have your Q. We want to check to see if it's conservative or not. So since P of x and y is equal to x minus y, and q of x and y is equal to x minus 2, then you can take the partial derivative of p with respect to y. Well, to do that, you need to hold x fixed. So when you're taking the partial derivative of p with respect to y, the derivative of x is 0, and the derivative of negative y with respect to y is negative 1. So we found the partial derivative of p with respect to y. Now, let us take the partial derivative of q with respect to x. This is equal to 1. In this case, we hold all other variables fixed, and we take the derivative with respect to x. The derivative of x with respect to x is 1, and the derivative of constant with respect to x is 0. But please pay attention here. You have a negative 1 and you have a 1. They are not equal to each other. Since the partial derivative of p with respect to y is not the same as the partial derivative of q with respect to x, you conclude that F is not a conservative vector field. You can take a look at the visualization as well. So if you use a 3D visualization, here you have this vector field with the first component x minus y and the second component x minus 2, and z is equal to 0 because we are looking at this in 2D. So take a look at the behavior of this vector field. You can just visualize this in 2D like this. So basically you have your x-axis, you have your y-axis, and this is the behavior of this vector field. You can take a look at the arrows, and as you can see, the arrows are going all this way. So again, this is an example of a vector field which is not conservative. So for this vector field on the given domain, you cannot find a potential function. So if you can restrict the domain somewhere somehow, you might be able to find potential function for some vector fields. So on the exam, if I ask you to define a vector field which is not conservative, you can use this example or any similar vector field that behaves like this.